Propositional equivalence. That's what we are going to learn in this video. As we learned in the previous videos, that compound propositions are made from primitive compositions or propositional variables along with logical operators. We denote the propositional variables with letters such as P, Q, R, and S, such as P, Q, R, and S, and these are the logical operators or the disjunction and the conjunction and the negation here. Okay, so we use propositional variables along with logical operators to form compound propositions. These compound propositions take truth values, either true or false, because each of them is a proposition, and we know that a proposition is a declarative statement that take either true or false. And as an example, in the last video, we have constructed the truth table of this particular compound propositions. We call it truth table. Okay. In this section, we will learn how to decide that a given two propositions, whether they are equivalent or not, logically equivalent. What is logically equivalent means? It means they agree on their truth values. But before we start doing so, let us learn what a tautology and a contradiction means. In fact, a tautology is a proposition which is always true. Here we go. A tautology is a proposition which is always true. For instance, P or not P. The logical operator or will give you true if one of the propositions at the side is true. And now we have P and not P. One of them must be true because they are opposite for each other. And therefore, P or not P is true, as we see it here in the table. Here we have P or T or F gives true. F or T gives T. So this is a tautology. Also, a proposition is called contradiction when it is false all the time. So a proposition is always false. It's called a contradiction. And here we have an example. P and negative P. The AND operator will give you false if one of the propositions at the side is false. Now we have P and not P. So one of them has to be false because they are opposite. One of them is true and the other is false. So the combination we have is false. So again, true and false is false. False and true is false. So this proposition here is a contradiction. Now, what's about the contingency? A contingency is a proposition which is neither true, neither tautology nor a contradiction. And we have already seen such one. The proposition here, this compound proposition, is a contingency. Okay, so we know now what is tautology and what is a contradiction. Okay, let us see more examples about tautologies and contradictions. Now let me take this please first. Okay, now let us see about this compound proposition P and Q. P and Q, we know the truth values, what they are. If P then Q, if P then Q, here we go. Now to obtain the truth values of this compound proposition, we will go from here to here, from this to this, with using the conditional statement. Okay, so true, if true, then true, the result is true. So we get true. False implies false, give us true. False implies true, give us true. And false implies true again, give us true. Now we notice that the truth values here are all of them true, so this is a tautology. Okay, let us see about the other compound proposition. We have P, here are the truth values of P, and we have P or Q, we take the negation, P or Q, and here is the negation. So if we have true, we get false, true, false, true, false, false, true. Now to obtain this, the truth values of this compound proposition, we must go from B to not P and Q, and we will join them with a conjunction, with an and. We will join them with an and. So we will say true and false gives false. False, true, sorry, and false will gives false. False and false will gives false again. False and true will gives false. Therefore, this compounded statement is false all the time, so it is a contradiction. Great. So far we know what is a tautology and what is a contradiction. Oops, sorry. Okay, now we will learn what does it mean for two propositions to be logically equivalent. Simply, they are logically equivalent if they agree on the truth values. If one of them, if both is true or both false. Now, this is the compound proposition here. Okay, they are two compound propositions are equal, are equivalent, sorry, logically equivalent, if and only if and only if they have they agree on the truth value. They agree in the truth value, on their truth value. Okay, now again, P is logically equivalent to Q if they have the same true value. But we learned from the last video that the biconditional P and Q will be true if both P and Q have the same truth value. So this is when this is true. When this is true, let me write it this way. When this is true, then P and Q are logically equivalent. And this is another way to write logical equivalent proposition, Q, P if and only if Q. Okay. Now, how do we decide whether a given two compound propositions are logically equivalent or not? In here, in this example, we will show that P, if P then Q, is equivalent to not P or Q. To do so, here in the truth table we have P and Q. Okay, what do we need to compute this? We need to compute not P, so we have not P now. To compute not P or Q, so we go from here to here and join them together, but with an or. So we will say true or false? True. True or false? True. False or true? True. False or true? True. Good. Now, what's about the conditional statement P gives Q? We already know these values. So now notice here, the values here and here, they agree. And that's what we mean by their truth values agree. Therefore, I shall write here now this statement P. So I would like to write it P gives Q if P then Q is equivalent to not P or Q. We will use this 2 times later in this video. So I will call it for a while. Maybe we will use this name equivalence star. Okay. Now, how we decide in general how two propositions are equivalent? We use truth tables or we use some laws. One of the very helpful laws to do so are the Demorgan laws. Demorgan laws are simple and very helpful. Okay. Notice here what this Demorgan law says. First, Demorgan law says, if I have, so I will talk about this now. If I have P and Q, a statement, compound statement, P and Q, and I want to negate that statement, what I do? So I want to take this statement and then do the negation for it. The answer will be is to distribute the negation over both of the two statements. Okay, so we will have not, sorry, I want the blue, not P, okay, and sorry, not P, not Q, but then this logical operator will be changed to OR. Good. Same thing if we do it for negation of P or Q. This is the second law of Demorgans. So we will distribute not P, not Q, but we will change this operator from OR to AND. So these are Demorgan's laws, and they are very easy, very helpful, and very important. Now, we can prove Demorgan laws, but here we will demonstrate the proof of the second law only. So let us go and prove this. And the first law is left for you to do. Now, to be able to do so, we need first to compute the truth values of this, and then which is given here now, and then compute the truth values of this, which is given in purple, and it is here. So let's go and do them. Okay, now we know the truth values of P and Q, and then P or Q, it is known for us. To go from here to here, we just do negation. So true will get false, true, false, true, false, true, false. It is just a negation. So we got the truth values of the first proposition to the left. Let us compute the other the truth values of the other composition. We need here to compute not P. So we have P, true, true, false, false. So the negation will be false, false, true, true, and not Q, as you see here. We get it from true, false, true, false, true, false, and then we have false, true, false, true. Now to obtain that, we will combine these two together, but with an AND, So we say false and false will give us false. False and true, false. False, true, and false will give us false, and true and true will give us true. Now, notice here that truth values of this proposition and the truth values of this proposition are the same. So they coincide, so they agree. Therefore, these two logical statements are equivalent, and then we get the proof of this statement here, Demorgan's law. Okay, let us see another example where we prove that some propositions are equivalent. In here, we will show that what is so called the distribution law. We will prove it is true. But first, let me explain what is the distribution law. Let me write this here. So if we have Q and R, both of them is a proposition, and I want to take that and make a disjunction with another proposition, which is Q. Make a disjunction with the Q. Now, this is equivalent to what? I will distribute. Now notice this disjunction goes over Q and R. So we first do Q and R and then make the conjunction. So we will distribute the conjunction and the Q over Q and over R. And we will keep the conjunction here. So we will have Q or P. So one of them is P. Sorry, I must forgive me, please. I must use for this letter here P. So let me repeat that, please. So let me fix that, please. This is P, and again. Okay. So we will distribute P. We will distribute P or Q. So we are distributing P and or, and here P or R. Okay, so we do them this way, and then we make a junction. We keep that junction as it is. So we distributed P and the or over Q and R, and we kept the conjunction and. To prove they are true, now first we will go and prove. Sorry for that. We will find the truth values of this, which is here. To be able to find it, we must go and find the Q and R. Okay, and this is Q, this is R. So Q and R, true and true is true, true and false is false, false and false is false and true is false, and so on. Okay, now to find this here, we must combine P. We must combine P with Q and R. So we will have P or Q and R. So we will have true or true, it is true. True or false, it is true. True or true, it is true. True or false, it is true. False or true, it is true. False or false, it is false. I did something. I should not. There are too many columns actually. Let me repeat that. There is some spot which is wrong here. True and false, which is true. True or false, which is true. False or true, which is true. False or false, which is false. False or false, which is false again. And false or false, which is false again. Good. Now we will work to get the truth values of this proposition here. So to get it, we need to have P or Q, P or R. So P or Q, we get them from here, P or Q. P or R, we get them from here. And you know how to get these things. Now, to obtain the truth values of this, we must join these two things together with a conjunction, with an and. So we will see true and true is true. True and true. True. Again, true and true. True. True and true. This is true, true and true. True, true and false gives false. False and true gives false. False and false gives false. Now, look at the truth table of this proposition and the truth table of this proposition here. And now match them together, you will find them the same, and so on. They are the same, all of them. They are the same. Therefore, we get this true. We get this equivalence to be true. According to this method of proof, we can prove many logical equivalences. For example, here, if we have P and true, then the truth value will be the same as the one of P. Why is that? Because if you have P, we have and conjunction, and we have true here. P and true. If P is true, then we get true. Let me write that. Like if we have P and true, it gives, see, if we have true for B or false, let's see what we get. So we get this, and then we get a true, and we get false. But this is the same as P, so it is P. Similar thing, if we use P or false, P or false, so we have true for B and false, or false or false. So what we get, true or false, it is true, and this is false, and this isn't the same as P here. So we just proved that. Now, P or true, the disjunction, the or, will be true if one of the proposition at the side is true. So whatever P it is, then we get true. So remember this, we will use them. P and F, the conjunction, if it has an F at one of the sides or both, then the result is F. So whatever P it is, P and F is F, is false. Okay. This is trivial. P or P. P and P is P. The negation of the negation is P. P or negative P. P and negative P, they have opposite truth values. So one of them is true, and we have a disjunction with a true at one of the sides, so we get true. Now, P and not P is false for sure. With an and, a conjunction, if we have a false at the side, then the result is false. But P and not P, they have opposite truth values, so one of them must be false. Okay. And commutative laws here, which shall be trivial. P or Q, it is the same as Q or P. Same thing for and. Associative laws, this is the one we talked about. So whether we go P and Q, then and R, is the same as if we do it from the other, from the right. I mean, Q and R, then and B. Same thing for or. P or Q or R is the same as Q or R, then or Q. Distributive laws, we have already talked about this one, and here we will make a distribution for this over Q and then over R. Here we got it, over Q over R, and then this is kept as it is. And absorption law, I will let you think about this one. Okay, more logical equivalence. Some of them I found some of them interesting, and some of them less interesting. We already know what this thing is. P gives Q is equivalent to not P gives not Q. This is the contrapositive. So this is the conditional statement, and this is its contrapositive. Remember when we said we assume when it gets cloudy, it rains. So we say if the sky is cloudy, then it is raining. This is sky cloudy, then it is raining. The contrapositive, which is equivalent to this statement, is to say if it is not raining, then the sky is not cloudy. So these two things, they are equivalent, and it's a contrapositive. They are contrapositive for each other. I like this one. Look at it. It's if P then Q, or P implies Q. This is a statement. How do we negate such a statement? How do we do the negation? We do it this way. P that comes first, we will use that in a little while. We just put it as it is here. And then add and Q. So the negation will go to Q. So the negation here will go to Q, and this will be changed to end. Okay. Here. What's about this? We talked about this is biconditional. P gives Q and Q gives B, so it has two parts. B gives Q and Q gives B. This is an and. Okay. And this is also interesting. B if and only if Q. This statement is true when both are true or both are false. Now, if both are true, then their negation are both false. So the biconditional here will be true. Okay. Or this is a double contrapositive. You may look at it this way. And this is the negation of the contrapositive. It looks like kind of similar to that. The negation went to the other side, but this logical operator stays as it is. And I will leave this for you to look at. Okay. Let us see now an example where we will prove logical equivalence, but without using the truth table. We will use the laws we learned. So we want to prove this logical equivalence here. See how we do it. Okay. The negation. So negate. We have already seen it. So we give the negation. Okay, sorry, we done something before. We need to use an equivalence that we have already seen, which is P gives Q, B gives Q, is the same as not P or Q. We just have already proved this, so we will use it. So from here to here, we are using this. It says in the book it is example 3. This is done example 3 in the book. So now what we do next? We will distribute the negation. We will use Demorgan's law. Remember, distribution, the negation is not for free. Once you distribute the negation, you will change the operator from disjunction to conjunction, from or to and. Now we distributed the negation. Negation of negation gives P, and this is still here. So we're done. We have reached this one. So this one and this one are equivalent. Let us see the example, the next example here. It asks us to prove this statement below here. Okay, so we will start with this one. Now, first thing we'll do, use the Demorgan law to distribute the negation. So we will have not P and not this parentheses. Here we go. The parenthesis here is here with a not in here. But remember, we changed the or to and. Okay. Now we will distribute, use Demorgan's law again, the second Demorgan's law. We will distribute, so not P, we get it here, and then we got not Q. But see, the and is changed to or. Now the next step, this gives P, not Q is waiting here, not P is waiting here. Now we will use distribution here. We will distribute this over that, and then over this. So we'll have not P and not Q, and this is stays as it is. Not P and not P and P here, not P and not Q. Okay, not P and P, one of them is false, and we have and, so we have a false. This is one of the identities we have already seen, and this stays as it is. So we have now, we used here, we changed place here, this one to this one. Now we have not P and not Q or false. This is one of the identities, or false. So the other statement will decide what's happening. So it is this one. So to be more precise, we have seen that P or false, this is the same as P. It is, we call it an identity. So this takes the place of P, and now we have reached what we want from here to here. Great, and the example is done. Now, one last thing here is to prove this is a tautology. We want to prove this is a tautology, which is its values, whose all values are true. And we will not do it using truth table. We will use it, prove it using the equivalence, the equivalences we learned. And okay, let's see what we do here. Remember this rule which says this equivalence P gives a Q is equivalent to not P is equivalent to not P or Q. So we proved it in example 3 in the book. So we will use it. Now, this stands for P, for this P here. Okay? And this stands, sorry, let me use another color. This stands for Q, for this Q here. So we will have not P or Q. So now we will, okay, let's pay attention to what's happening here. Now what we do, we use Demorgan's law. So we will make distribution. We will distribute this negation here and negation here, but this will be changed from and to or. So we have not P or not Q. So now we have or. Now it does not matter which order you put them. If you have all logical order to be or and, then you can play with the positions of the propositional variables. So if we will play with them, we would like to make this P and this P come together. P or not P. This not Q and Q come together. Now we learned that P and not P, or sorry, P or not P is always true. Q or not Q is always true. So we have true or true, we get true. So this compound of proposition is always true. So it is a tautology indeed. And this is comes to the end. Okay, thank you.